So you graduated from UT. When was that? When did you graduate?
2015.
2015. Okay.
Yeah.
Okay. And have you been with Simtech ever since, or
From 2017 around, we opened SimTech, a startup.
okay, very good. Very good. Hello, Con. How are you?
I'm doing good. How are you?
Oh, I'm fine. It's good to see you.
Yes. Yeah, I want to learn geothermal. This is a hot topic.
It's a hot topic. Absolutely.
Mhm.
Good morning, everyone.
Hey, good morning. How are you?
Good, John.
Thank you for pointing me in this direction. I think this will be a great talk.
I think there's a lot of synergy here, and their focus has been in some things that you're involved in as well. So I think it's great.
Yeah, absolutely.
Some very, very interesting emerging software
That's cool.
and workflow. So that'll be great.
Yeah.
We cannot hear you. You try to say something?
No.
Yeah. No, we're just saving up for the main event. We'll give it let's give it 1 minute longer. People are still joining.
Morning, Ali.
Good morning, John.
Well, good morning, everyone. Maybe we'll kick things off here. And Dr. Yu and I just hope everybody had a good summer. And welcome to his presentation. And for those of you who have not met Wei Yu, he is the CTO for Simtech LLC. And his research interests include EDFM technology for modeling complex fractures and EDFM-AI for automatic history matching. And if you don't know what EDFM is, you will within the next hour, I'm pretty sure. So Yu has authored, Dr. Yu has authored or co-authored more than 200 technical papers and 3 books. And that's pretty amazing for someone who graduated in 2015. And he holds a PhD degree in petroleum engineering from the University of Texas at Austin. So Wei, the floor is yours. Please proceed. Share your screen and let's proceed. Thank you for doing this.
Thank you, introduction, Professor. Let me share my screen. Oh, hold on. Now it's okay?
That's great.
Okay, good. Morning, everyone. I'm welcome to attend this seminar. Today, I will share our EDFM method. We developed this method more than 10 years. And first, we focus on the fracture modeling. And also, we did several years for geothermal simulation. I will share some case study. Hopefully, you can learn something. So today, first, I will introduce the this is the EDFM, and also second, I will talk about the ZFRC AI and the EDFM AI, based on AI technology to drive fracture modeling and reservoir modeling, to do benchmark history match. And third part, I will show some case study for geothermal application. We know fractures reservoir simulation is not easy to do, and we really want to do more accurately and more efficiently. That's more than 40 years ago. We have like dual porosity, dual permeability model. So this method, I like that a lot. It simplify very complex reality to more like simple. It works very well. But however, we found it's some case, maybe dual porosity doesn't work well, maybe a little bit more over simplify the fracture complexity, especially if we want to model hydraulic fractures. This slide shows the comparison between different methods. So in order to model 3D fracture, my meaning like 3D, like you have some deep angle, not always the vertical fracture. So that's like a dual porosity, dual permeability model. So it's really fast, but the accuracy, you will see that it assumes fracture everywhere. So it's difficult to more accurately handle the 3D fracture. As for unconventional, we have like a lot of commercial reservoir simulator using local grid refinement. But most commercial reservoir simulators, they're using simple grid or structure grid. So it's really difficult to model a little bit more complex fracture. Only can handle parallel or orthogonal fracture. So the accuracy is good, and the efficiency is quite difficult because you will see a lot of small grid nearby fracture, and also difficult to handle 3D fracture with deep angle. And then we have some like unstructured grid simulator can try to model like 2D fracture complexity. So 3D still no way. So the 2D, you will see a lot of smaller grid nearby fracture. That also result in the efficiency is not high. If your fracture aperture is too small, like several millimeter, so it's also difficult to generate this smaller grid. So in default fracture aperture is about 2 feet. So that's the reason we work on EDFM since 2010 until today, the 13 years. So this is a very good method to model like 3D fracture. And we do not need like local grid refinement. And also we have applied several US patent. The EDFM is not so difficult. So mostly like geometry, like 3D fracture, is like a polygon, and you have your 3D model, and the algorithm will identify each fracture will be cut how many small fracture piece depending on the matrix box. For example, the fracture 1 will be cut 3 small fracture segments, and the fracture 2 is only in this box. And after this in the physical domain, we know we have 2 fracture, but in the computational domain, we will have like these 4 fracture segments. And then in the reservoir simulation area, we know we have a non-neighbor connection. We have something keyword, and we know the transmissibility. For example, the fracture 2 will communicate with this matrix block, but they are not a neighbor. This is called non-neighbor. And in order to model like geothermal or like DTS fiber, we need like thermal temperature behavior simulation. So that's the reason we have like not only flow EDFM based on Darcy's law to calculate the transmissibility, and also we need to have thermal EDFM based on the temperature. That's like thermal transmissibility. So all the transmissibility calculation, we have like three types. One is you have a matrix to the fracture, and also like in the single fracture plane, you have different fracture segments that called fracture connection. Third one, like in one block, you have 2 fracture that called fracture intersection. So the transmissibility is quite easy. You can see this equation is only depends on 2 grid, like distance, common area, and also the permeability. So we also published the book, talk about all the details for this equation. So currently, I think I saw a lot of EDFM paper, many university, many people work on this method. Last one is like a fracture to well. We have like wearable index based on Peterman equation. So you can see the EDFM is only deal with the geometry. It's nothing related with the mobility. So it worked for like gas reservoir, oil reservoir, condensate reservoir. So because only like geometry. So you will see the EDFM one big advantage compared to the structure grid. You will see we do not need the local refinement. We just embed or push or embed this complex 3D fracture, and then we generate 2 grid like matrix grid and fracture grid. It is similar like a dual porosity model, but it's different because the dual porosity model just calculate a shape factor, but we calculate the transmissibility. So this you will see there that you do not need to touch or modify the matrix grid or geo model, not like on structure grid. So that will result in you will have much less number of grid to model fracture. It will run much faster. So we benchmark a lot for this method with local grid refinement from a single well or multiple well. I think a lot of people benchmark this method. So each method has an advantage and disadvantage, but based on benchmark, we found if the grid size, if the grid size too big, maybe have some accuracy issue. So most time the grid size maybe like 50 feet or 20 feet is no big problem. And so that reason we benchmark like this is a tight gas case. We published this paper several years ago, and we can get a very good match between local refinement and EDFM because the grid number EDFM is much less. That result in the much faster, 20 times faster compared to the local refinement. We also tested a lot of other cases. If you have more fracture, you will have much less grid number, and maybe the speed up can be 100 times. And also benchmark thermal EDFM. This is also, you will see this is local refinement. This is EDFM, is no refinement. And we benchmark like not only pressure distribution and also temperature behavior. So we also can get a very good match between EDFM and LGR method. This is one case to show what's different the EDFM and the dual porosity model. I designed a simple case. You will see the 2 well, like 1 injector and 1 producer. you will see several natural fracture. But you can see there is no natural fracture connection between injector and producer. So you can imagine if you do water flooding, so maybe there is difficult to have water breaks through from the producer. But you will see the EDFM capture this very well. You can see the water saturation is difficult to flow to the producer, and will stop here. But you will see the due porosity model will overestimate the fracture connection, because in this grid we have like 2 fracture, but the due porosity doesn't know that, just upscale to the single fracture. So that's the key that maybe show you a better understanding of the EDFM can more accurately model fracture connection. We also collaborate with Saudi Aramco. We try to test the limit, how big number of the fracture we can handle with our EDFM, because we saw a lot of paper, most of the paper work on a little bit more research based. So we try to model like a more field scale application, and you can see we try to model 400 well. So this is a very big model, and because in the future especially for the unconventional, we have maybe each company has a lot of well. Maybe we want to model not only single well or maybe several well. We try to model several hundred well, try to understand the like oil saturation or gas saturation. I think it's better to do refill or infill well drilling. Currently, most commercial simulator is difficult to do that, but we test we can handle this well. It's 400 well, and hydraulic fracture about more than 44, like 800 number. A natural fracture we put like 1 milli natural fracture. The total grid about 42 milli. We run 32 CPU. In about 10 days we can finish that. So that means based on the EDFM, we can consider this a very big model to do very big number of fracture and well. And another friendly of EDFM, we developed this EDFM like a bridge. We can couple almost every fracture simulator, like kinetics, Gopher, most people used, and steam plan. And we can get their geometry, because this is a fracture simulator. We know the geometry, we know their format. So we can directly load their format to the software, and we can output to the third-party reservoir simulator. Because all these reservoir simulators, they have a keyword non-neighbor connection. So we do not need to modify their source code. We just change their keyword. So with the EDFM bridge, all this fracture simulator and reservoir simulator, they can couple very well. But we also have our own fracture simulator called ZFRAC. And also we work with Echelon, Stone Ridge company. And this is a purely GPU reservoir simulator. And we can, the key purpose we wanted to make sure fracture simulator, reservoir simulator can run much faster. I think the speed is very important for the future, no matter unconventional and geothermal. I don't like a very slow simulation. So that reason I like purely GPU. And also in ZFRAC, we also have a parallel. The EDFM, we also have a parallel. So we are also work on the GPU, EDFM, and the ZFRAC. Here I show one case study. You can see the speed. This is the one shale gas reservoir. You can see the geo model, and you have a lot of natural fracture network. And if without the GPU, if we use CPU simulator, we need to do upscaling. We need to upscale the geo model vertically, maybe to 10 layer around. So total grid number is about 200,000. If larger than this grid number, sometimes it's running very slow. So you see this well about 100 days production. If we run EDFM with the CPU reservoir simulator, it average about 30 minutes. 30 minutes to run one case. But with the GPU reservoir simulator, it's only about 40 seconds. So that give me a very big surprise. So the GPU hardware can speed up this reservoir simulator, fracture simulator, really a lot. So almost the reservoir simulator can be real time, like 100 days production, 40 seconds, you can finish a simulation. So that can make out a lot of workflow can be changed totally. And also we tested another case because we know the unconventional horizontal well, we can model multiple well. Before that, we only can focus on single well. Maybe you also read a lot of paper, many people only focus on single well. So difficult to consider well interference and fracture network. But now we test this kit like a CPU reservoir simulator with 8 years of production, because most unconventional well, their age about maybe 8 years, most larger than 5 years. So if we run CPU reservoir simulator with the EDFM, if without EDFM, of course we cannot model this because you will see some natural fracture network, right? So if without natural fracture, you can use the LGR, but with the natural fracture, you must use the EDFM. So with the EDFM, the CPU reservoir simulator is around about 2 hours. 2 hours to finish this case. So one day you only can run maybe 4 times. So that's very slow. But with the GPU reservoir simulator, we use the NVIDIA A5000. This is not a very good GPU, but it also work. It's okay. It's only about 8 minutes. 8 minutes. So you can imagine 2 hours, one case. Here is only 8 minutes. So 2 hours you can run many cases. So that I'm very happy. We try to develop the fastest reservoir simulator and the fracture simulator in the world. So we can run many well and run many times. So based on this speed, we can extend the EDFM a lot of different applications. Unconventional, you can easy to do multiple well, not only single well. And the conventional fracture reservoir like water intrusion. So that's also we can do very well. And also CTUS, if you have some fault activation and natural fracture. So we also can do CTUS. But today I will show several cases about the geothermal application. So the second part is about based on AI, because AI machine learning is very hot. It's very useful. It can help people a lot. I don't like manual history match with completion data and production data. So I really like use a couple AI with the physical model to do a lot of things. So that reason we develop ZFrag RE, the software. We know there is a lot of fracture model, fracture simulator. I don't know which one is the best, but we try to do something different. And I didn't see any fracture simulator can handle 3D natural fracture. Most fracture simulator can only handle 2D, only call vertical fracture. And also like horizontal fracture, like we call bedding layer. So that's a two feature I didn't see anyone can do that. That's the reason we try to do first hydraulic fracture simulator can handle this very well. And after that, we can do, because EDFM, we can handle this production. So here I show one field case with the bedding layer, because the bedding layer can reduce the effective fracture height because the leak off, and also we have some 3D DFN activation. And based on the ZFrag, we couple with AI because the ZFrag running very fast. Each stage is about maybe 10 to 30 seconds. It's about a second, not most commercial fracture simulator need maybe 30 minutes to run one stage, but now we only about 30 seconds. So that reason we can do a lot of history match, not only focus on single stage, we can do the whole well. So the do a whole well, and we can do sensitivity study with this parameter like short number, short diameter, and friction coefficient. And then we can run maybe 20 or 30 times the fracture simulation, and we can get the best match with the pumping pressure. And then we can move on to the reservoir simulation. So in the reservoir history match, same thing. I don't like a manual history match, so we do automatic history match. So we can do a single well, multiple well with the EDFM, and because we know the fracture is dynamic. When you do hydraulic fracture model, that tell you all the liquid and the sand can go there, but with the production, the fracture will be closed to some extent. So we call effective fracture or DRV. And with different time, maybe fracture will close further. So the fracture geometry not static, it's dynamic. So that's the reason we need to do something like a cutoff to make sure the hydraulic fracture model maybe at the beginning too big, and then we need to automatically cut off this very big fracture length at height to a little bit small to match the production. That's the reason the GPU reservoir simulator is very important. Before that, is one kit running need several hours, but for this loop, we need to run at least maybe 200 times. So if one kit like several hours, you need about maybe 1 or 2 months to match this production. But now you do not need 1 or 2 months, maybe only need several hours because the GPU speed up is huge. So that reason we can do a lot of multiple well history match. I will show one field case study recently we did. And this case show like one pad with 4 horizontal well. I will see this is like seismic, and you can see a lot of natural fracture. I know like in the US, like Marcellus Shale, Austin Chalk, maybe Permian Basin, and they have something like a fracture network. And based on this seismic, we can create a natural fracture network because the operator, when do the well drilling and also identify this fracture network is more accurate. So we need to capture this fracture network because they have a lot of fracture heat or fracture driven interaction and or well interference. We need to consider this network. So after that, we know the fracture simulation, the most, it will take a long time to do data preparation, like pumping pressure and pumping rate and sand concentration. So we try to make the fracture simulator more user friendly, so we can automatically load this this well, this completion data. So you will see this 4 well. We have each well is about 20 stage. So if you manually prepare this data input, it maybe need several days, but now it's all automatically loaded in this software, and then you can see each stage the running is about 10 seconds. So that this year we try to do real time fracture simulation, and each well is about 3 minutes. So you will that speed can use the AI to do multiple run, and also not only focus on. I talked to many people, especially completion people. They said most commercial fracture simulator will only run 1 stage or maybe 3 stages, but now we can run every stage. I can see the activity, the 3D natural fracture network has well interference. And we use the AI with the DFARC. We try to match every stage pumping pressure, and you can run 30 times. And we totally did 4 well. We run about 2.5 hours, 2.5 hours. We can finish all calibration. So if you use like you can imagine if 1 stage run maybe 30 minutes, 2 hours maybe run 4 stage. But now we can run all this totally about maybe 80 stage. Yeah. And after fracture simulation, we need to calibrate with the production. Here, this pad has about 2 months production. Each well, this you see this shale gas reservoir is a gas production, and with the GPU reservoir simulator, it's still NVIDIA A5000. It's 0.4 million grid number. It's about the running time is only 2 minutes. So 2 minutes you can finish this one run. But with the CPU reservoir simulator, I think maybe at least 2 hours run. So that you will see after 1 kit running, we can visualize the pressure distribution in this fracture network and also drainage volume at a different time. So with the EDFM-AI, the important thing, we can do history match automatically. So you do not need to manually do history match. It really depends on your experience. So I don't like a single match because it will be non-unique and unbiased. So that we can run multiple match that can make sure the best match can be a little bit more representative. And based on my experience, I will run 500 cases. So 500 cases, totally about 6 hours. So about 1 day, we can get a 42 history match solution. So you can see the bottom hole pressure match for each well is pretty good. And also we try to match water flow back. because the shale gas reservoir, they have some water flow back. So after this multiple match with the 42 match, we can understand better for the effective fracture length and height, because we know the fracture will close due to proppant embedment or other reason. So you will see the 42 history match solution. We can understand each well, what like P10, P50, P90, what's the P50 value of the fracture length. Like effective fracture half length for each well, we can see like 60 meter, 47 meter, like 34, 46. So that's very important to calibrate this model. So then we have this model, then we can do better optimization, how to increase the effective length. Maybe you need a proppant, you need to redesign some of cluster spacing and pumping rate and set concentration and other things. So that so if you have very good model validation, calibration, then you can do a lot of things, optimization for well spacing and completion design. And the fracture height is quite small, like average about maybe 6 meters around. So after this multiple match, we can have better understanding of matrix property and fracture property. I didn't show all, and then you can do EUR forecasting 20 years, and this is 4 well. Then you can get a P10, P50, P90, because it's running very fast. So that's can give you very quick EUR prediction. So the total workflow you will see only about maybe 1 day, but if without EDFM, without a GPU, that maybe need I think at least 1 month or maybe 2 months. So that's I think that's today I would like to share this. This is the fastest simulator in the world, and the technology, and we can run a lot of cases very easily. So then they show the pressure distribution in the complex fracture network. You see the natural fracture connected to the well, and also the drainage volume after 20 years. So last application, I want to show several like geothermal. Because we don't have a real geothermal project. This is like a very hot topic. I know there are a lot of things for design, evaluation, drilling, and completion. But my side, I want to do some more contribution about the simulation part. So like geothermal, I think from a simulation point, is same thing with unconventional, how to handle this more realistic hydraulic fracture network and natural fracture, based on the field scale. So I read a lot of paper. Most of the paper only focus on several fracture. They use unstructured grid to do a lot of research base, but there is difficult to show the field scale geothermal simulation. So that reason we need to extend the EDFM to thermal EDFM, and to handle this more realistic geothermal simulation. So here I designed one synthetic case, because we don't have a real project. If we have a real project, we can put all the real well trajectory of completion design and network, and then we can to do optimization maybe before geothermal completion. Here I show like 2 well, and each well about 20 stage, and each stage is 6 clusters. We have another this fracture geometry is we didn't run fracture simulation. We have another tool to generate a fracture quickly. Here we consider like hill biggers, and this is model size, this is low permeability, well spacing about 400 feet around. And then we put some 1,200 randomly distributed natural fracture network to, we can assume natural fracture closed or opened in a model that's easy to play. And you can see with the natural fracture, maybe the well to well connected through this natural fracture and hydraulic fracture. And then we set up some basic other input for the geothermal simulation. So and then we also develop another tool to identify the fracture connection or fracture connectivity. Here this is a term we define called inner connectivity. Like you have a two well hydraulic fracture and natural fracture. Here we assume a natural fracture activated, and you can see the number of connected natural fracture and divided by number of total natural fracture. In this case, is inner connectivity about 96%. So I know the natural fracture connection depends on the density, orientation, and the size. So that's a lot of uncertainty. So that reason we have EDFM, we have GPU, we have AI, so we can do a lot of sensitivity study, have a better understanding what is this connection on the geothermal application. And you can see the red color, these natural fractures, they all connected each other with the hydraulic fracture. And the gray color is the isolated natural fracture. So I think for the geothermal application, this natural fracture connection tool is very useful. And then we can run this simulation very quickly, and we run about 1 year, 10 year, 20 years visualization of the temperature behavior. And in the visualization, we can separately to see temperature in the fracture network and also in the matrix. And you can see because of the well connection is not very strong. Some part is very strong, some part is not connected well. And you can see is a very highly non-uniform distribution of the water transport. You can see these three parts have early water breaks through, and the other part is not connected well. And also we can visualize the cooling zone just without the fracture, without the matrix, just see the temperature. This is like a cooling zone propagation. And you can see mainly like three parts have quick breaks through, and most part is not connected very well. And also we can output the production temperature behavior. So that case show the EDFM with the GPU reservoir simulator, we can do a very big field scale or more realistic fracture network simulation. I think that's maybe we try to contribute for the geothermal area. And then we can do some sensitivity study for the natural fracture density, how to improve this uniformity of the water injection to the producer. And we can design some lower DFN density is about 600 natural fracture. You will see much small number of red color natural fracture. And also this is like base case 1,200 and double high 2,400 natural fracture. So they connected almost everywhere. So this is a simulation without comparison. You can see like lower natural fracture density, and these two parts is like maybe connected very well. And this is like base case. And this you will see if you have more than 2,000 natural fracture, the cooling zone propagation is more like uniformly. So that will be very good for the geothermal efficiency. And also the key learning, like if you have a very good fracture connection, depending on the higher fracture, natural fracture density, then you have a very large, higher production temperature. And then this is very good for the geothermal system efficiency. Yeah, this is like one case. Second case, like Utah Fault. Utah Fault is a great project. A lot of data published and public in the website. So we open the website, we collect some data from Utah Fault, like permeability, heat capacity, thermal conductivity, and especially the radar temperature is initially is not a uniform distribution, and you will see is a highly non-uniform distribution. But I don't know the reason, but we got this data from the website. And this is like a basic model for the Utah Fault, but we don't have the real well. Here we just designed two synthetic horizontal well, and we didn't get the realistic DFN input. We randomly generated some DFN for the Utah Fault, but the other parameter we use Utah Fault data. And we designed the two well, like each well like a 40 stage and 6 cluster per stage. We randomly put like 2,000 natural fractures. So that's if we have like a more realistic Utah Fault, the real well and the DFN, I think that will be much better. Then we can do based on the ZFRAC AI, we can do a very good quick validation of the real well. But here is no validation. We just put a synthetic well, synthetic hydraulic fracture, natural fracture. But you can, but here you will see the natural fracture side that maybe very good, and you have very uniform cooling zone propagation, and the EGS the efficiency will be very high. So I really like to follow this Utah Fault project. We can move on if we get more data. We can easily change this model. The last one, I want to show the EDFM not only for this synthetic model, but we can do like a realistic geology model. So this model like about 1 milli fracture grade, 1 milli grade is highly heterogeneous, 3,000 hydraulic natural fracture, and we design like 1 injector and 2 producer. And this is the more just like if you have petrol model, we can direct load this petrol model to the ZFRAC and EDFM and reservoir simulation. And this porosity distribution is highly heterogeneous. And then you will see this 3 well after ZFRAC, and then we get this kind of geometry. And then we can run reservoir simulation, and you can see this pressure distribution in the fracture system and pressure distribution in the matrix. And also we can visualize the cooling zone in the fracture and in the matrix. So that's the last case show the EDFM with and this thermal EDFM. We can do a realistic geo model, 3D natural fracture, and the real well. So, but we to be honest, we don't have a real project to do better validation and optimization. So hopefully we can get some real data to do this geothermal application. So I think time is okay. So a quick summarize. So the ZFRAC RE with the EDFM is very useful to do quick fracture design and simulation. And AI is very powerful to run multiple well history match from maybe 2 months to reduce to 1 day around. So that we can run many well very quickly. And also fracture connection is very important for the geothermal. So we have this tool, but we need maybe real data to do better test. And we have like EDFM book and AI EDFM AI book. So all the details you want to repeat this method is quite easy. So we write all the details in the book. Thank you, everyone. Welcome any comments. Yeah.
Hey, Wei, thank you. Very, very impressive presentation. And it's generated a few questions. I don't know whether you can see the chat or whether you'd like me to read the questions.
Oh, yeah, okay, yeah.
Um, and the first question comes from Mark McClure, and Mark indicates that it appears to me that EDFM does not avoid the need for local grid refinement. If the radius of investigation is small relative to the size of the mesh, then EDFM without local grid refinement will be extremely inaccurate, just like a conventional reservoir simulation. This issue will be a serious issue in applications like shale or EGS. How would you respond to that?
Yeah. This is a very good question because when we do EDFM more than 10 years ago, we tried to benchmark a lot, but we really found EDFM also has some accuracy issue, especially for the shale, like the permeability is very small, like 10 nanodarcy, or maybe 50 nanodarcy, but larger than 100 nanodarcy is quite okay. Because if you have very small permeability, your mesh or your grid size should be very small. Because of the big assumption for the EDFM, we assume the pressure gradient is linear. So for tight gas, tight oil, that's no big problem. So that reason, if you want to use a very small permeability, you must use a very smaller grid size, but this will result in the efficiency not high. So the EDFM, the value will be lost. So that reason we still want to use the big size, like not like 10 feet, we use 100 feet, but we still use the local refinement. We need to couple EDFM with the LGR. We also published one paper, but this one, even coupled with LGR, you still have LGR disadvantage. We have a lot of refinement, but we try to have a smart design with the LGR. We do not need a local refinement too much. So that I think we are still ongoing work on this, and we try to couple EDFM advantage and the LGR advantage to balance accuracy and efficiency. Yeah.
So this is Mark. If I could just follow up on that. I mean, you're saying that you can use this for EGS, but EGS heat conduction is very slow, and so it seems like you need a lot of local grid refinement. You need something to get an accurate solution. And also, I mean, you're saying it's faster with EDFM, but I think the reason it's faster is because you're using a coarse mesh. I mean, if you just ran a conventional reservoir simulation with a coarse mesh, it would be fast.
Yeah. So
I have a very basic question that I'd like to ask. In your model, in the graphs that you show, it doesn't show that you're including the effect of stress shadowing, the interaction between fractures in horizontal wells as you move from the towards the heel of the well. If you're not including that, then how accurate are your results?
Yeah, that's a good question. Yeah. In the US, most shale, the stress between minimum and maximum not too big. So the stress shadow you will see the curve, the fracture. So the model is there. I didn't show the Permian Basin or other basin the study, but in the international shale reservoir, the stress difference is very big. So it's sometimes it's all the planar fracture. It's difficult to have non-planar fracture. Of course, you also can handle different stage stress shadow. That makes the running maybe a little bit slow, but quite okay. But I know the fracture simulator, the validation is quite a challenge. So it's not an easy job. Yeah.
But look, even if the difference between the stresses is small, when you create hundreds of fractures in the formation, and you put millions of pounds of proppant inside these fractures, you create a large stress shadow because of the added mass into the formation. So even if the stress difference is small, by the time you get close to the middle and the heel of the well, you have created large stress shadows.
Mm-hmm. Yeah. This summer I also work with some operator together. So I really think currently the maybe fracture model theory maybe not enough to capture more realistic phenomena. So that's I think I like Mark Law. I almost read his post every post. I learned a lot from him. I think that we from a fracture model part we still need to work hard to improve the theory. So
And the
not
other
like,
question,
not like reservoir simulation is more mature, I think.
the other question I have is that when you talk about such extensive coverage and modeling and so many grids and so many blocks, how long does it take you to enter the input data for every element of this formation? And the input data, you know, formation properties, fracture properties, reservoir properties, how long does it take you to enter the input data in order to do the simulation?
Yeah, that's currently, especially we work with like Middle East, Argentina, some international shell. They have very higher resolution, like geomodel input, like stress, Johnson modulus, Poisson ratio. And for reservoir part is like porosity, saturation. So these geologists to do this work, and we just get the model from our input. So for the history match, we need to tune like a permeability, because permeability is difficult to measure, and also like a fracture effective length, height, and conductivity. So mostly we have less than 10 parameter uncertainty. We can do like use AI to do automatically. So that's we need to do not manually. If manually, that's almost no way. That's too difficult. But this AI we also work on more than several, maybe 5 years. So that, but we still work on that. We maybe if you have more uncertainty, we need a more better AI maybe.
So a couple of reasonable suggestions there for additional work. And Dmitry Chuprikov, Dmitry's concerned about the fact that you really don't know the three-dimensional distribution of natural fractures. How does this impact the accuracy of your simulations, or can you overcome this with AI or something similar?
Yes, that's I'm thinking this is a lot, because I think hydraulic fracture is a big uncertainty. It's difficult to characterize, even with the fiber and a lot of things. More than 10 years, we are still working on that. But for natural fracture, this is another big challenge. The number, the size, the orientation. So we know there is like a DFN workshop I attended several times. The natural fracture, they did a lot of them, like side make, a lot of things. I try to also learn, but I don't know what they did. But based on my understanding, the orientation, the density may be quite good, but the size is really, really difficult. So that reason, from my side, I think the size we can do uncertainty. For example, you give me the orientation, you give me the number, I can make a size automatically longer, shorter, and try to link with the production. And also natural fracture like aperture, not aperture, no, the permeability. So that's the thing, because the natural fracture, the permeability and connection, that's very important for the production. So that's we need to validate to this property. But geologists, they know the orientation, the density. But this is still a very challenging topic. If we don't have anything, we just randomly run many cases. But maybe we can read other paper, know this area a little bit better. We have this orientation, like Permian Basin, maybe more uniformly, like Marcellus Shale. We have something other crop. So we need a. So that reason in the AI workflow, we can play the DFN, the number, the size, the orientation, all that we can involve. Try to before that, we don't have a GPU. It run very slow. We only run maybe several hundred, but with the GPU, we can run several thousand. So that we can maybe better capture the uncertainty of the DFN input.
May I make a comment?
Yeah.
It is an amazing simulator. I'm very impressed with what you've done. But with the issue of natural fractures, the only thing you know about natural fractures is from the various wells that you drilled, and then you can create those information, which is mostly a guess. The same thing you do with the dual porosity and dual permeability. We calculate the dual porosity parameters or dual permeability, lambda, omega, kappa, all of that, and then you create it throughout the reservoir. So I agree with the question that is getting natural fractures to that distribution and defining the natural fracture is mostly a guess. You know, you're expanding data from few wells into the whole reservoir. We have done that before in our simulators. When we develop simulators, what we took the values from the well bores, the various well bores, and we have 10, 20, 100 well bore that you logged or you worked on, like that picture you were just showing. And you create it over the whole reservoir. So it depends on what you assume in the kriging model that you use. There's a lot of parameters that you change. We found out it may be easier or as good to calculate the dual porosity or dual permeability parameters, omega, lambda, and kappa for dual permeability, and omega and lambda for dual porosity. And you do the same thing again. You create it over the whole reservoir, and you assume that the kriging was done correctly. You can try multiple or different types of kriging to reach different results. So, but I have to say, it's a really amazing simulator that you showed us. I'm very happy to see what you've done. Thank you very much for the presentation.
Thank you, Professor Soliman. So I want to add one more comment for the natural fracture, especially in the unconventional. I think even this study, I think the natural fracture size a little bit too big. You can imagine the size bigger than the hydraulic fracture. I think the natural fracture, you can imagine when you do fracturing job, maybe the natural fracture will be opened, right? But maybe sand is difficult to fully support the natural fracture open, maybe only small part. So that's the reason even we have this 3D natural fracture, in the reservoir simulation part, I want to put more maybe a smaller effective area. Otherwise, overestimate the contribution of natural fracture. Because the sand is difficult to, even the hydraulic fracture is a sand like this, but the sand is hard to go to this high in the natural fracture. That's my learning. I want to make a natural fracture is smaller in the production.
So maybe we could just proceed on with a couple more questions here. I mean, we're running out of time. Wenjin Jin is asking something slightly different than these other folks. He's curious about the GPU solver, and he suggests that GPU definitely has value for certain numerical methods, but for finite element methods, he's indicating that you assemble the matrix for iterative calculation, and that's usually done in CPU. You usually do in CPU, and this will significantly slow down the calculation. So, do you have any comments that you'd like to make in this area about GPUs?
Yeah, these are expert questions. So I'm not an expert for GPU solver development. So for reservoir simulation, we tried it works very well, but for finite element method, I don't know too much about this. Yeah.
Good answer. Good, honest answer. Now, and then Dimitri has another question. And does the aperture of the natural fractures depend on the flowing fluid pressure? And if yes, how do you model the aperture changes?
The hydraulic fracture and natural fracture aperture is we input about several millimeter. So we didn't change the dynamic. We didn't consider dynamically change of the aperture. We just changed the permeability, because in the reservoir simulation we call fracture conductivity. Conductivity equal to aperture times the permeability. So the simulation we put a constant aperture, but we change the permeability.
Okay.
Yeah.
Okay. So you're modifying the conductivity.
Yeah.
Yeah. Comments indicating good presentation, which we all agree with. And then another question on stress shadowing, and I think we've talked about it in a couple of ways. Now, are there conductivity? It goes back to Dr. Danishi's question. Are there conductivity changes associated with fracture interaction?
The fracture conductivity, yes, fracture conductivity is not always constant. So that reason is for fracture conductivity is difficult to achieve infinity. It's all finite conductivity. and we call fracture closure effect. So with the production, with the pressure, and with the pressure drawdown, the fracture conductivity will be closed. Either natural fracture, hydraulic fracture may be different. So so that reason maybe if the fracture closure is more strong, the production will decline a lot. So that's the reason for the future, the shale reservoir production, we really need a maybe powerful proppant to make sure the conductivity didn't change too much. Recently, we work on one project. We have about 8 years of production. We use one fracture geometry and one fracture conductivity change. It's difficult to match. So that I propose a new idea. Maybe we need to consider different stage of the well. For an early stage, maybe 3 years, and maybe 3 to 5 years second stage, maybe 5 years to maybe third stage. Different stages, maybe they have a different effective fracture geometry, and maybe they have a different fracture conductivity change. So that's we try to work on that.
Okay.
If one well you have very powerful conductivity, no big change, and the geometry no big change, perfect. I think that will maybe the unconventional product will be doubled or tripled. That's perfect. But I don't know how to achieve that.
Okay. And Jean-Marc, I apologize. I probably didn't ask your question very well. I mean, does the conductivity also vary as a function of temperature?
Oh, sorry. For temperature part, we didn't consider the conductivity change. Yeah.
Okay.
Yeah.
Okay. And then Luke Frasch, Luke, it's a long question. Why don't you unmute yourself? And we've only got 1 minute.
Yeah, that's meaning like what's the range of the fracture conductivity. I know a lot of people work on the field lab to measure fracture conductivity, but that value is very big. It's difficult to directly use in the reservoir simulation. For reservoir simulation, the first we will do a sensitivity study, try to understand what value is infinity. For example, in Marcellus Shale, I did a lot, like from 1 to 10 millidarcy feet. 10 millidarcy feet is almost infinity. It's no production difference between 10 and 100. So that's the simulation value, not the real field value. And or maybe underground, we don't know. So that's the reason the model is just a representative. So that's the reason different like shale gas, shale oil, maybe different property or shale reservoir, they have different infinity conductivity. I just make an example like Marcellus Shale, like 1 to 10, that's good in range. But most effective value like 5, maybe 5 millidarcy feet, not like 10 is too big.
I think we're probably out of time. I know there were some additional questions and comments, and I apologize for not getting to them. I encourage you to follow up directly with Dr. Yu if you've got more comments. But very enjoyable and impressive simulations way. Thank you so much for presenting.
Thank you, everyone. Thank you, Professor. Yeah. Have a good day. Yeah.
Thanks all.
Excellent presentation. Thank you.